All right, all right. Okay, so we were working towards our beautiful shortcut. This is awesome stuff. So everybody click those close. Let's take a look where we were yesterday. We were talking about Riemann sums, right? But we were, yikes, we did all that. This is what we were looking at right here, right? We were looking at trying to use Riemann sums to come up with a solution to something like that, right? We want to find the area under f of x equals x squared from a to b, okay? And so we decided we're just going to slice this thing up into uniform slices. Delta x equals b minus a over n. We're going to use a right sum because those are the most convenient, okay? So we're just going to be, we're going to add up the area of each individual rectangle is just going to be f of x sub I. That's going to be the height of the ith rectangle then, if we use a right sum, times the width delta x. And so we could, we could do some substitution there. Delta x is b minus a over n, so we plug that in. F of x is x squared, so then we can transition from here, f of hand is just equal to hand squared. We expanded that out and we started to get something that looked, more messier, but it started to look like something that we could maybe do something with a little bit, right? So where'd we leave off? We left off here. We were going to try to do a couple things. We've got this b minus a over n that we're just going to pull out in front of all the action. And we're going to split up this sigma, right, this sum, into separate terms, right? We've got three separate terms there. We'll sum them individually, right? We'll sum term by term. So the first one is just going to be the sum of a squared plus, so here's this plus sign. Then we've got this second term. Well, the only variable of the summation is I. So all this other stuff is actually, we can pull it out in front of the sigma. There's no i's in any of these factors right here. So they come out front. And then we're just left with the sum of I, right? Here's our next plus sign. So this is the plus sign connecting us to the third summation then, right? Again, we've got all this stuff, this b minus a quantity squared over n squared, no i's, so we can pull that out in front of the sigma. And then we just get the sum of I squared. Now, those are summation formulas that we know, right? We already revealed those the other day. The sum, well, maybe you can remember them. See if you can remember them. What's the sum of some constant as I goes from 1 to n? N times the constant, right? Think about what that's saying. The sum of a squared as I goes from 1 to n, well, there are no i's in that. It's just going to be, every term is just going to be a squared, isn't it? And I'm going to have n of those terms. So that's what we get from our first term. The sum of a squared just becomes this. I'll try to link these together here a little bit. So let's see, how about if we, the sum of a squared, the sum of a squared just becomes that, a squared times n, right? But I've got this n on the bottom then. If I multiply through by this factor that's out front, I've got this n on the bottom, and what's that? Oh, maybe. Oh, that's the outs. What the heck? Hang on. We better look at this. I got to see what's going on here. What the heck? B minus A. Oh, yeah, we distributed that n through, didn't we? Okay. Yeah, we distributed that n through everything. We left the b minus a out front. And all we did was this, right? To get down to this step, we just took this 1 over n, and we're just going to distribute that to each fraction. Okay? Make sense? So then we get a a squared n over n. There's my first term, right? Good, the n's cancel. What about this guy? Well, the sum of I from 1 to n is just n times n plus 1 over 2. Remember that one? That's one of our summation formulas. It's just given to us. If we distribute this additional n from outside, that's going to give us an n squared on the bottom, right? This n becomes an n squared. And then when I multiply all these things out, I could cancel one of my n's, top and bottom. I could cancel that 2, and that's going to give me something a little bit simpler. Let's just kind of track. Let's just kind of track where that leaves us as we move along. So we get our b minus a. That one just becomes an a squared. What's all that stuff going to become? Well, if I cancel the 2's and I cancel an n, I just get that, don't I? Everybody agree? Just doing a bunch of algebra. Just a bunch of algebra. Okay, then how about this last one? Okay, this last one, again, we distributed that n all the way over, which made that n squared and n cubed. I've got my b minus a squared, and the sum of I squared from 1 to n, remember that was n times n plus 1 times 2n plus 1 over 6. So I can cancel an n. What's that going to give me? So I'm going to get my b minus a squared. I've got an n plus 1 times a 2n plus 1. And then on the bottom, I've got a 6n squared. Okay? Just a lot of algebra. But something good's going to come out of all this. So now what? Okay, if we split this up, this common denominator, that just looks like 1 plus 1 over n, right? And this one over here, if I expand this out, if I FOIL this out, I'm going to show this little step here real quick. If I were to FOIL this thing out, this is going to give me 2n squared plus n plus 2n, so plus 3n plus 1 if I FOIL all that stuff out, right? Divided by 6n squared. Well, if I split those terms up, 2n squared over 6n squared, the n squareds cancel and I get 1/3, right? 3n over 6n squared. 3 over 6 gives me a 2 on the bottom. I've got 1n left over stuck on the bottom, right? And then the last one, 1 over 6n squared. Okay? Now, what was so good about that? What's so good about that? Look at that. Look where my n's are showing up. This is the right sum as a function of n, and n is the number of rectangles, right? Don't lose track of what n actually is. What do you think? They're all on the bottom, and if n is equal to... There's the trick, right? What if we take the limit as n goes to infinity, right? We're going to take the limit of this right sum as n goes to infinity, and look what's going to happen here. Yeah. Look at that. Look at all the good stuff that happens there. So the actual area, the true area, is equal to the limit of the right sum as the number of rectangles goes to infinity. And in that case, every term where I have an n on the bottom, those are all going to get driven to 0 in my limit, right? Those are all going to get 0. And so who are the survivors? Just everybody else. So when all the dust settles then, that's all that's left behind, right? I just get a 1 from that factor. So I get a squared plus a times the quantity b minus a times 1 plus b minus a quantity squared times 1/3. That same thing as being over 3. Okay, now what? Well, now we just need to add all this stuff up, right? So I really just need to get a common denominator. Okay, so what I do here? I guess I just distributed the a and canceled the a squareds. I expanded out the b minus a quantity squared, right? Last step now would be to get a common denominator. right? If I want to get a common denominator, I'm going to have to multiply top and bottom by 3. So that's going to be a 3ab over 3, right? So I get that. Agreed? Combine like terms. And what does that look like? 3ab minus 2ab is just minus ab, right? Okay. So don't I get that? Everybody agree? Okay, what is that? Do you recognize that? Distribute that out. What am I going to get if I do, though? Anybody predict? That's a pattern. That's the, we're going to do a factoring pattern in reverse. That's the result of what factoring pattern? Do you remember? Well, yeah. It's a difference of cubes, isn't it? Isn't that what we get when we factor a difference of cubes? A cubed minus b cubed, or b cubed minus a cubed in this case, right? B cubed minus a cubed would be b minus a times b squared plus ab plus a squared. But we could, I mean, we don't have to remember that. Look, I could just, all I've got to do here is just distribute. If I distribute the b and I distribute the negative a, what am I going to get out of that? So I've got my 1/3 out front times, if I distribute the b, I'm just going to get b cubed plus ab squared, right? Plus a squared b. If I distribute the negative a, I'm going to get a minus, oops, wrong color. Oh, thanks. I'm going to get a minus a squared b minus a, hang on. Oh, I forgot the minus ab squared, didn't I? Whoops. Minus ab squared minus a squared b minus a cubed. Well, look at all the cancellation, right? Those guys cancel, those guys cancel. I just get b cubed minus a cubed, right? Okay, that's significant, right? So what's that telling me then? That's telling me that if my answer looks like this, right? We said that's b cubed minus a cubed. Well, that's the same thing as b cubed over 3 minus a cubed over 3. Okay, that's interesting. That's interesting. There's a way we could write that. We can write that as in this way, and when we write it in that way mathematically, what that means is this is going to be the difference between this expression evaluated at b and a. That's what that means, right? This means I'm going to plug the b in and then subtract what I get when I plug the a in. Okay? So this is a notational shortcut, but why is that so significant? Think about the function that we started with. We started with the function f of x equals x squared, right? So how do we get from f of x equals x squared to x cubed over 3? You guys have made that connection. What is it? It's the antiderivative. Isn't that crazy? That the antiderivative is what's connecting the result of all that algebra to the function which is describing the area, x squared. Isn't that incredible? That's the first fundamental theorem of calculus. That's what it tells us. That if we want to evaluate the definite integral, the integral of f of x dx from a to b, then the answer is the antiderivative of f of x evaluated from A to B. That's it. You get it? So this just means f of B minus f of A, where capital F is the antiderivative. Okay? And so our final answer is what? Well, I mean, we can plug in, well, that's our answer, but now we can be specific and we could try an actual integral. I think I want to go back for just 1 second. Does this part up here make sense? Yep. Yes, exactly. And we have a power rule now for definite integrals, right? If f of x is x squared from what, back when we did antiderivatives, before we started getting into sigmas and areas and stuff like that, right? You guys would have told me that if f of x equals x squared, then the antiderivative is just going to be, you guys would have said this, right? The antiderivative of x squared dx is x cubed over 3 plus c, right? Well, this part right here is the antiderivative, right, to within a constant. So if you just abandon the c, that is going to be, if we make this a definite integral, let's just say we're going to go from 1 to 2 or 1 to 3, how about? If we go from 1 to 3, then our answer is equal to x cubed over 3 evaluated from 1 to 3, which just means 3 cubed over 3 minus 1 cubed over 3. So what is that? That gives us 27 thirds, which is 9, right? Minus 1/3. So that's just 26 thirds is our exact area if we did that problem. Look how fast that is. Okay? Make sense? Now we'll do some examples. So this, right? That's we just derived the trick. Now we get to use the trick, the first fundamental theorem. Okay? So what about this? The anatomy of a definite integral. We kind of talked about this, but here it is on one slide for your notes. So we'd say we got the integral symbol. We've got at the bottom, we have the lower limit of integration. At the top, we have the upper limit of integration. Those are numbers, right? Those are x values that are encapsulating an area, right? They're telling us from what x value to what x value are we adding up an area under the curve. F of x is the integrand. That's telling us the shape of the curve under which we're adding up area. And dx is just the differential of the independent variable. Often I just call it the variable of integration, right? Okay, so let's try an example. Let's try this one. Okay, so how am I gonna use our newfound trick, first fundamental theorem, to find this area? What's the definite integral I set up that represents the exact area? Integral? Integral of square root of x. How should I probably write that? 1/2. Okay, so x to the 1/2 dx from 1 to 16. Okay, so what is the antiderivative of x to the 1/2? 2/3 x to the 3/2. Good. Okay, so we get 2/3 x to the oh my goodness. 2/3 x to the 3/2, and we're going to evaluate that from 1 to 16. Okay, I got a question for you. What can I do with that 2/3? What are my options? I could include it in my calculations, but I could also just bring it out front, right? You see why? Because the 2/3 is going to be a factor. Like I'm going to get 2/3 times 16 to the 3/2 minus 2/3 times 1 to the 3/2. We'll just factor the 2/3 out. It's the same multiplier, right? Same coefficient in both terms. So isn't that a little more efficient just to do that? We're going to get 2/3 times whatever we get from our, when we evaluate our definite integral. Okay. So then this just gives us 2/3 times 16 to the 3/2 minus 1 to the 3/2. What is 16 to the 3/2? 64, yeah, right? Because that's all we're doing is we're square rooting 16 and then cubing that result, right? 16 to the 1/2 is 4, cubed is 64. What's 1 to any positive power? 1. So we get 2/3 times 63, and 63 over 3 is what? 21 times 2 is 42. Did I do that right? You better check my work, but that's our area. Okay, we can check it. Let's just check it on Desmos and see. Or on your graphing calculator, right? I'll show you both ways. 1 to a negative power it's still going to be 1. Yeah, it's still going to be 1. Yeah. 1 to any non-zero power is 1. 1 to any non-zero power. 1 to the 0 is gosh, it's 1 also, isn't it? Yeah, you're right. So 1 to any power is 1, isn't it? Okay. Didn't think about that. Oops, wrong tab, darn it. Okay, so in Desmos, let's see, what was our integral? I got to go scoot up a little bit. Okay, there we go. So in Desmos, we would just do this. Integral of x, whoops, from 1, I just typed int. Otherwise, you can get it from the keyboard down here, but it's just faster to type int. That's just a shortcut. From 1 to 16 of, now you got to make sure you're putting this inside the integral or it won't give you a good answer. X to the 1/2 dx, whoops, got to get out of the exponent, dx, there it is. Okay, now look what would happen. So it is 42. If I go too far, like if I scoot over 1 more to the right, I guess I can't anyway. It's foolproof. 42. Okay, make sense? That's how we do it in Desmos. How about on your graphing calculators? All right, you can do this 2 ways on your graphing calculators. So we can graph it. We could go up to y equals, and we could just type in like square root of x, or x to the 1/2. And then I can go, okay, so if I've got something graphed, I'm just going to go set my window to go from, I want to go from 1 to 16, right? So I'm just going to go from 0 is my x min. I'll make my max something like 20. How about? Actually, I'll just do 18. And then I'm going to, once I've set my window like that, I'm just going to hit zoom fit. Remember this? Zoom fit is zoom 0. Just so it graphs it nicely in my window. Right, when I hit zoom fit, what that's doing is it's fitting the vertical constraints of the window, y minimum to y maximum. It fits that for my function to the x constraints that I chose, the width of my window. I chose from 0 to 18, so it's picking appropriate y values, so it graphs my function nicely over those x values, spreads the function out. Okay, it's real convenient. Now I would just go, anytime I want to do something with this, I go to the calc menu. So second, calc, which one do I want? 7, yep. So I'm going to go 7. My lower limit is 1. Enter. My upper limit was 16. Enter. What do you know? 42. Okay. And it even reminds you what your limits of integration are. Okay. That you don't really have to go through all that though. On these fancy graphing calculators, you can just go to the math menu, and I'm just going to scoot up. Oh, there it is. Finite integral right there. Number 9. Okay. That looks familiar. From 1 to 16 of integral of square root of x dx. Enter. Good luck. 42. Okay. Make sense? Okay. Very handy. All right. So some properties of definite integrals. I just want to take a look at some of these because these are, you already probably know most of these are just common sense. Okay, what's the first one say? We can evaluate definite integrals term by term. So we can break up definite integrals just like we could with antiderivatives and derivatives. I could break this, if I have a sum of terms, I could break that into separate definite integrals. Okay. What is this one telling me? The red one. Well, I can pull a constant out front, which you guys already know, right? You can pull constants out in front of integrals. Indefinite integrals, antiderivatives, or definite integrals, they work the same. What is this guy telling us? Actually, I'm going to scoot over to this page. I added a few more here. So we'll look at these. These have to do with how do we calculate area, these first 3. So let's take a peek at those. Okay, what about that first one? Oh, darn it, that's supposed to say, oh my goodness. I got to fix this. That's supposed to be, so I probably got to go back to this page and fix it too. My goodness. Why can't things just ever work out? That's supposed to be an A. And if that's an A, okay, never mind, not on that page. How come that's 0? Yeah. If my left limit of integration is x equals a and my right limit of integration is x equals a, that's an infinitely narrow band of x values. It has no width, so therefore it has no area. Okay, common sense, makes sense. Okay, what about this one? This is a little bit strange. Okay, this defines how we, this sounds like I'm from Green Acres here, but a lot of times people in math will say this is how we reckon area. We reckon area as positive when it's above the x-axis and when we're adding it from left to right. So if A is greater than B, and let's just say hypothetically that f of x is a function that sits above the x-axis, then the green integral would represent positive area. Okay, the orange integral would represent the opposite of that, right? So the integral of f of x from b to a, if I'm going backwards, that's going to calculate a negative area. Here, I'll demonstrate it for you. So let's just take an example where we can set up any function we want to. Let's just make this really simple. Let's just make it x squared. And if I'm going to add this up from A to B, so from A to B, that area is, it's 2/3. That blue area is 2/3. If I go, let's just go from like, how about if we go from -2 to +1, now the area becomes +3. It's all above the x-axis. Okay, what happens if I flip those limits of integration around? Instead of going from -2 to 1, let's go from 1 to -2. What happened? Now the area is negative because I added it up in the negative direction from right to left. Okay? What would happen if we made this function negative? If I put a negative out front, what's that going to do to the area I just calculated? It's going to be positive. How come? Because you see what we did there? Here, let's unmix our limits of integration again. Let's go from -2 to +1. Okay, what's that telling us? Well, that's telling us that an area added in the correct direction from left to right, if it's an area that's below the x-axis, it's negative, right? Because that's how we define areas: positive above the x-axis, negative below the x-axis. Okay, so if we're adding it from left to right, that's negative area. If I add it from right to left, what's it going to become? It's going to be positive because we're adding up a negative area backwards, which makes it positive. Okay? Just to prove it to you, there it is. Now that's positive area. Okay? That's because that's just the convention, and thank goodness it works that way, because it needs to, right? It needs to. Otherwise, calculus wouldn't work, and the math guys wouldn't allow this. But it wouldn't work for all the things that we need it for. Like if we're calculating the work done on an object, right? We looked at the baseball. Remember, we looked at the baseball. When we hit the baseball, we calculated the work was the area under that curve. Well, the work done can be negative too. Work done can be negative. Like, for example, if I'm going to do, if I throw an object up in the air, then the force is acting downward, right? Okay, so the displacement is in this direction, but the force is acting in this direction. And so what that means is the force is technically negative in that situation, right? And so we get a force profile where the force would be a function underneath the x-axis, and we're doing negative work, which we are doing. Because didn't I tell you, I know there's a lot of physics, but didn't I tell you that the work done was the change in kinetic energy? Kinetic energy is the energy of motion. The faster something moves, the more kinetic energy it has. What's happening to the kinetic energy after this ball leaves my hand? Starts off going pretty fast upward, right? But it's slowing down as it rises, and so it's actually being robbed of energy. So gravity is doing negative work on the object. So we have to have the capacity for calculating negative work. The math gods did that for us. Work area is negative if it's underneath the x-axis, right? Okay, so it all works out the way it needs to. Question? Does it what? Yeah. Mm-hmm. Yep, works on all functions. Okay, so moving on. What about, okay, and so we looked at those, right? Those just define how we calculate area. Area is positive if we're adding it, if it's above the x-axis, added from left to right. Okay, what about this guy? What's this saying? The integral of f of x, definite integral from a to c, plus the definite integral of f of x from c to b equals the definite integral from a to b. Okay, what's that doing? Do you see that that's just adding up adjacent areas? That's all that's doing. If the upper limit of one definite integral corresponds to the lower limit of the next definite integral, then the right edge of this area becomes the left edge of this area, and we're just encompassing just one big area then, right? Everybody see that? Okay, so I'll give you a demonstration because you can get kind of tricky with this one too. So for example, here we've got, oh, okay, good. Yeah, I spent a little time putting this together. So here we're calculating areas. I'm going to call this first area is from A to B. So that's going, A is -1, B is 1, right? should I flip those around? How about if I flip those around? So this matches, yeah, I'll do this. Hang on. Can I not grab this thing? Oh, there we go. Okay, let's do that. And let's put C in the middle, how about? Because that's how the integral was set up, right? Okay, so the first integral from A to C, I got these backwards then, didn't I? Yeah, shoot, just a second. Let me fix these. So we'll make that a C. We'll make this C and that a B. So this exactly matches what you guys just saw, and we'll make that a B. Okay? So what does this first one stand for then? Integral from A to C in this case is going to be from -1 to 2, but let's make that a 1. Okay? And that is 4. Okay, let's shade that and see what we got going on. So that's, oh, darn it. You know what I'm going to have to do? Oh, my goodness. I'm going to have to, I'll tell you what, I'm going to have to, sorry, but the B is going to be our middle variable now. That messed everything up. I can't do it the way I thought I was going to. Right? So B is our middle variable, A is our left, C is our right. Everybody see that? A is -1, B is 1, C is 3. So the integral from A to B, that's from -1 to 1 is 4. There's what that looks like visually, okay? The integral of my function from B to C, that's going to be from 1 to 3. That's that area right there, and that's -4. Okay, so then what should the total area be? 0, which it is, right? Everybody see that? Okay, but we could mess this all up. What if we make, would this work, do you suppose, if I made my middle variable actually to the right of C? Like, let's flip these around. What if this becomes 3 and that becomes 1? Now the area from A to B is 0. The area from B to C is 4. And the area from A to C is also 4. How come? What did it do? You see what I'm getting at here? This is the area from, how can I write this down? Right, this is the integral from -1 to 1. The second one is the integral from -1 to 3. This is the integral from 3 to 1. So we're adding up area backwards, right? And this is the area from 1 to 1. Okay? That's okay to do. I mean, that looks a little bit odd, but if I just get rid of this for a second, what did we say here? Right? We just said we're doing, in this case, from 1 to 3. Plus the integral from 3 to 1 must equal the integral from 1 to 1, right? Or it's -1, sorry. Everybody, because 3 is the common limit of integration. As long as the upper limit of this one is the same as the lower limit of this one, they are always going to add areas. They're going to be additive, right? How come? Because here I added up a great big positive area. Here I added up a negative area, right? And those combined to give me the net area. What happened when all that stuff, right? See what I'm saying? It's like saying I over added the area and then I subtracted a little bit to get back from my upper limit from being from 3 to 1. So the signs still work out. It's crazy, right? As long as these two match up, there's no implication here that this that the common limit of integration even has to be between A and B. C could be outside of it. It doesn't matter. Because of our conventions about adding up area, the math gods ensure it always works regardless, which makes this a very versatile property. Does that make sense? I got rushed at the end there, but you get the idea? Okay. And again, we can see that. There's the first area, right? That's from A to C. Now here's the area from, it's back, well, we can't see it because it's backwards. I get a negative area from 3 to 1. And when I add all those up, that's the total area. A bunch of it got subtracted. Okay?